NASA's brand new telescope is about to do in 1 month what would have took the Hubble Space Telescope a century to do. That telescope is called Roman, and it's set to launch really soon on Sunday the 30th of August 2026. Roman is the follow-up to Hubble, so it's exactly the same size, so we're going to get the same level of detail in its images, but it's been designed to look at a much bigger area of sky in a single observation, with a field of view 100 times bigger than Hubble's. That's why Roman is going to be put to work doing surveys, splitting up the sky into little patches, taking an image of every single patch of sky to meticulously record what we find there and slowly build up a map of our universe. So while all the images taken by Hubble in its 36-year lifetime have only covered less than 1% of the entire sky, Roman will cover 12% of the sky in just 17 months for one of its surveys, a feat that would have taken Hubble 1700 years. But it's not just about doing things faster than Hubble, it's about the new science, the questions we will be able to answer thanks to the data that Roman will give us. So, in this video, we're going to dive in and chat about 5 of the big science questions we're hoping to answer with Roman, from cosmology to supermassive black holes to dark matter. And if you want to know who the telescope's namesake was, Nancy Grace Roman, and why she's known as the mother of Hubble, or how Roman differs from ESA's Euclid Space Telescope, check out my previous video after you've watched this one, which I'll link in the description down below. But here, let's start with the first one on my list there. Is our best model of the universe wrong? Because those of you who've been around on my channel for a while know that I love chatting about the crisis in cosmology, where different methods are giving different answers for the rate of expansion of the universe, and the fact that we now have tentative evidence that the acceleration of the expansion rate of the universe isn't constant. It appears to be changing with time. And a lot of this research work hinges on our observations of supernovae, specifically a type of supernova that gives off roughly the same amount of light each time, so it's always the same brightness. So from how bright those supernovae appear to us, we can then work out, well then, how far away must the galaxies that they're in be? And we do that for a lot of supernova, and we use that to work out how fast space is expanding between us and those galaxies. So because light travels at a set speed, it takes time to travel through space. So the further away a galaxy is, the longer that light has been traveling through the universe. And so we're seeing galaxies as they were earlier in the universe's history, which means we can study how things change over time, including the expansion rate of the universe. Now, currently we've observed a few thousand of these specific type of supernova that we need to do this. But with one of Roman's surveys of the sky, we're set to detect 21,700 of this specific type of supernovae. That's about 10 times more supernovae than all the other previous surveys combined. Plus, we're hoping that Roman will be able to push back the distance that we're able to spot these supernova at as well. So hopefully it should give us a few hundred that went off, more than like 10 billion years ago, which is, much better than the handful that we have now. Maybe even a few dozen that went off more than 11.5 billion years ago. And it's getting more supernovae spread out over more of the universe's history that leads to better and more reliable measurements. That way we can work out whether our current best model of the universe that has this constantly accelerating expansion rate is wrong or not. Now, one thing we're going to have to be careful about after Roman launches is the inevitable increase of misinformation that's going to be online, with articles and videos just making up new discoveries for clickbait and views. We saw this after JWST launched, and let's face it, it's still happening with web news now as well. So I know that many of you are already wary when you come across big claims like, for example, NASA's Nancy Grace Roman telescope is set to explore dark matter and potential alien worlds in a headline. line. But thanks to Ground News, the sponsor that I've been working with for a few years now, I can immediately see that this is a news story that is legit. It's been covered by 58 sources from around the world, and that 94% of those sources have a high factuality rating. You all know that on my channel, like, the main goal is to try and make astrophysics more accessible for all of you. And I feel like that's what Ground News does with the news for me. They have these data-driven tools that helps understanding and staying informed with the news just that much more approachable. So I really like how you can compare the coverage across different stories with Ground News. So that Roman story, The Independent, went with the universe's greatest mysteries could be solved with NASA's new launch, whereas MIT Technology Review went with NASA's new dark energy space telescope can also detect killer asteroids, whereas NASA itself led with the human angle of NASA's Roman telescope to carry 1.35 million names to deep space. So you just get the full context of a story in one place with Ground News, which their bias comparison features summarize really nicely. But I use their blind spot feed the most because I find it really interesting to see which stories have been disproportionately covered by one side of the political spectrum. I've heard from so many of you that you also love Ground News as well, so if you head to the link in the video description down below, ground.news/Dr. Becky, or you can scan the QR code that's on screen, you'll save 40% on their Vantage plan to get unlimited access to all their features, which comes out at around about $5 a month. Those subscriptions help keep Ground News ad-free and free of any of the bias that comes with paid advertising. So big thanks to Ground News for sponsoring this video, and now let's dive back into our big questions that Roman will answer with the next on my list there. Where's the dividing line between planet and star? Because you can get stars so small that they're almost planets, but also you can get planets so big that they're almost stars. We call these objects brown dwarfs, and they're everywhere. They're anywhere from around 4,000 times heavier than Earth up to 25,000 times heavier than Earth, which means technically they are heavy enough to start nuclear fusion in their core. It gets dense enough there, but they're not heavy enough to sustain it. So they're kind of like failed stars stuck somewhere in between a star and a planet. And what we want to understand is why these form, like where that dividing line is between planet and star, so we can understand better how stars form and, crucially, how planets form. So Roman is going to hunt for these brown dwarfs using a survey known as the Galactic Bulge Time Domain Survey. Basically, instead of looking out to all the other galaxies out there in the universe, it will look inside our own galaxy, staring at the stars towards the center of the galaxy and watching to see if one of them flares in brightness in something known as gravitational micro-lensing. So this is when one star passes almost exactly in front of another, and its gravity briefly acts as a lens, magnifying the background star's light. But if that background star has a planet or a brown dwarf in orbit around it, then that planet or brown dwarf will tug on the star, causing it to wobble around a little bit. That wobble shifts the alignment of the two stars, meaning the lensing goes in and out of focus. It's called, and I kid you not, the Zalarap effect. Yes, that is a ridiculous word. Astronomy is rife with these, but really it's just parallax backwards. So the hope is that Roman is going to find over 10,000 of these brown dwarfs, these failed stars in our galaxy. And by comparing how often brown dwarfs turn up in the very dense center of our galaxy where there's lots of stars versus, towards the edge of the galaxy closer to where we call home, we can work out if there are conditions that are more likely to produce star with just a brown dwarf in orbit around it versus a star with a system of planets around it. But this method is not just sensitive to brown dwarfs. It can also catch planets smaller than Earth, down to around about the size of Mars. No matter how close to the star they orbit. Really, our current exoplanet detection methods are really biased towards heavy things orbiting really close in, so spotting an Earth-like planet is a little bit more difficult, but not with this method. So yeah, we'll find a bunch of brown dwarfs and understand better how planets form, which is cool, but Roman should also help discover similar versions of every single planet in our solar system. Moving on from the solar system though to the next one on my list there, how did supermassive black holes get so supermassive? We don't understand how black holes get to be as heavy as anywhere from 1,000,000 to tens of billion times the mass of the sun. The only way we know to make a black hole is when a star dies and goes supernova and leaves behind a black hole that's, say, around 5 to 10 times heavier than the sun. We think we know how they grow from there though, drawing in material into what we call an accretion disk and what the limits are to how fast they can grow. So you'd think, okay, star goes supernova in the early universe, its core collapses down, makes a black hole, say 10 times heavier than the sun. And then it just starts to grow from there, and then it ends up supermassive eventually. But the James Webb Space Telescope has been finding overmassive black holes in the early universe. They're too heavy, having grown too quick for how old the universe was when the light from their galaxies was emitted. We can see these black holes because the material spiraling around them is accelerated to such huge speeds that it starts to glow. So that's made people wonder, well, is there another way to form a black hole in the early universe? Instead of starting with something 10 times heavier than the sun that's formed in a supernova, maybe there's a way to make a black hole that's 1,000 or 10,000 times heavier than the sun that gives black holes a little bit of a head start when they start to grow to become supermassive. The problem is when we look into the distant universe, we only find the brightest of things, and the heavier the black hole, the brighter the light of the material around it. So we only will spot the most massive black holes with the James Webb Space Telescope. But to truly understand how black holes got so supermassive, you need to understand what their starting point is. Did they start at 10 times heavier than the sun or 1,000 times heavier than the sun? So you need to find the least massive black holes in the very distant universe, and we can't do that with JWST. What you need is Roman and its High Latitude Time Domain Survey. This survey won't cover a big area, it'll cover a small area, but keep coming back to that same small area over and over and over again to detect ever more distant things, but also detect if anything changes in that part of the sky. What we'll be looking for is something known as a tidal disruption event, or TDE. It's when a star gets a bit too close to a black hole, but not so close that it gets trapped there. Instead, it mostly escapes and in the process gets shredded apart, creating a beacon that we can detect that brightens over a couple of weeks before gradually fading away. And crucially, these tidal disruption events get more likely the less massive a black hole that you have. In fact, you have to have a mass less than around 100 million times the mass of the sun for this to even happen at all. If you have a more massive black hole, then that's just going to swallow that star whole instead of tearing it apart. So if you want to look for the less massive black holes, you need to look for tidal disruption events. Now, Roman should spot around about 100 or so TDEs during its initial 5-year mission. And it's by recording how many of these tidal disruption events we see at different points in the universe's history that we can track how they change with time. So if there is a steep rise in the number of tidal disruption events as we go to greater and greater distances or earlier in the universe's history, we know that there are more of the smaller black holes there, and the growth rate of black holes must be very quick. But if it's not so steep of a rise, then perhaps the growth rate isn't as quick, and maybe black holes are starting from that head start of a direct collapse black hole, maybe down into something that's like 1,000 times heavier than the sun. Enough of black holes though. Next on my list, can we hunt for exoplanets by taking a direct image of their reflected light? Because not only will Roman be able to hunt for planets using that technique that we talked about before, the Zalorap, but also it should be the very first telescope able to take a direct image of a planet using the reflected starlight off that planet. Now, yes, direct imaging of planets does exist already. It started back in 2004, and fewer than 100 exoplanets have been imaged this way since. But every one of those images, from JWST's first direct planet image in 2022 to those amazing time lapses that we have of planet systems moving in their orbits, none of those have used reflective starlight. They've been taken in the infrared. So So what you're detecting is like the leftover glow, the leftover heat from a planet's formation. It's not reflected starlight in the same way that we see the moon or planets in the solar system through telescopes. Because the big problem with trying to do this, and the next sentence I'm about to say will come as a surprise to nobody, is that planets are a lot fainter than stars, often 1 billion times fainter than their stars. So what you have to do is block the light of the star first with something known as a coronagraph. Roman's coronagraph instrument is designed to be around 1,000 times more powerful than any coronagraph we've had before. But even with the star's glare blocked out, the planet is exceptionally faint because it's such a tiny amount of reflected starlight. So it could be, over a month of Roman staring at one specific planet system to try and get an image of a planet. And even then, this won't get us an image of an Earth-like planet around a sun-like star. Instead, Roman will only be capable of taking an image of like a big gas giant planet like Jupiter. I say only, like this isn't like a massive engineering feat in itself, but this is the very first time that we're going to be able to do this. And really, Roman is going to act kind of like a stepping stone, a technology demonstration before NASA's next big flagship observatory, which hopefully will be able to take an image of an Earth-like planet, the Habitable Worlds Observatory. Now, I've made a video about habitable worlds before, which I'll link below if you want more info on that. It's not launching until the 2040s though. So for now, Roman's job is to close that technology gap between what's possible now and what we're gonna need for Habitable Worlds Observatory, so that engineers can prove that it works, and reliably as well, so that they can scale it up for what's gonna be needed for habitable worlds, so that we can get our hands on those Earth-like planet images we so desperately want to see. And finally on my list there, where is all the dark matter found in the universe? We think dark matter makes up around 85% of all the matter in the universe. But we still don't know what it's made of, because the clue is in the name. It's dark. It doesn't interact with light in any way, so it doesn't emit light or absorb light or reflect light so that we can detect it's there. But it does have mass. And Einstein told us that mass curves space-time. So even though we can't see dark matter, gravity still gives away that it's there. That's where this idea of lensing comes in again, but on a much bigger scale. When light from a distant galaxy passes close to another galaxy or a cluster of galaxies, that mass bends the light's path and acts as a lens. The closer the light passes, the more it bends. Us astrophysicists can then model for that bending and take away the contribution of the stuff that we can see, the stars, the gas, the planets, the dust. And what we're left with is how much of that bending is due to the dark matter, how much of it is there, and how is it distributed. Roman is expected to find around 160,000 of these gravitational lenses in its big survey of the sky, with a precision on the position of those lenses equivalent to resolving the width of a human hair from a distance of 2.5 football pitches away. And that precision is so important because smaller clumps of dark matter will bend the light more subtly than a larger clump of dark matter. So it means Roman is sensitive to smaller clumps of dark matter as well as the bigger ones. Those smaller clumps include the kind that we think came together in the early universe to provide the scaffolding for the first galaxies to form around them. And different theories of dark matter that, when it's made of different things, predict different sizes of clumps that you'll get in the universe, specifically like what's the minimum size of clump that you can get. So if you have heavier, less energetic dark matter, then you can get clumps forming that sizes all the way down to like the size of an asteroid. But if you've got lighter, more energetic dark matter, then you're going to have a much higher cutoff on the minimum size of clump that you can get. So not only will Roman be mapping out where all the dark matter is, Roman will also be hunting for these clumps as well. So hopefully in the future that will contribute to us figuring out what 85% of all the matter in the universe is actually made of. So there you have it, 5 exciting big questions that we hope Roman will answer. But let's face it, just like we've seen with Hubble for the past 30 odd years and with JWST for the past 5 years, the most exciting discoveries are likely to be the ones that we never expected. The serendipitous surprises that turn physics upside down. Constantly accelerating expansion rate. The light looks weird today. I feel like I've forgotten to do something, but everything is on. I think it's just because it's sunny. How is the temperature doing? Okay, we're still okay. At least over there it is. We call these objects brown dwarfs, and they're everywhere. And they're anywhere, but they're also everywhere. I wanna be with you everywhere. It's called, ow. It's funny how much I love planes when I'm on them, but hate them when they're flying over me.